on a project which was funded by Department of Energy named PSAP program. I'm currently assistant professor at mechanical and aerospace engineering at Cornell University, and my lab is focusing on problems that are tangent to this problem, biological flows, cardiovascular flows, and developing methods for such applications. So what I'm going to be talking about today is particle clustering. What you're looking at in this image is a turbulent flow at Reynolds number of about 1,000. And we have basically nickel particles of diameter 12 micron and released in this flow. And what we observe is that these particles tend to accumulate in certain regions of the flow. And you might be able to come up with an intuitive description of why this happens. But what I'm going to be trying today in this presentation is that can we come up with a mathematical formula to describe what we're observing in this image. First, I should give a disclaimer about what I mean by a new perspective. It's not meant as a self-glorifying statement. I gave it this presentation about 2 or 3 years ago, and Professor Andy Akrivas, that some of you might know, was among audience. So he started asking a couple of questions and followed up with several meetings. So we ended up probably having over 10 hours of discussion on this topic. And what I've learned during those conversations was thinking about formulating the same idea but from a different perspective. So that's what I mean by new perspective. All right, so what's the problem that you're trying to solve? If you take a turbulent flow, so here it could be in any number of dimensions, spatial dimensions. Here I'm taking a homogeneous isotropic turbulence in 3 dimensions, taking a slice of that, and releasing inertial particles in that flow. So particles could have different sizes, and depending on that size, you could observe different behaviors. So what I'm showing here is that if you start from particles that are fairly small, so their inertia or their relaxation time is much smaller than a time scale of the flow, you would get a homogeneous distribution. You could put it in plain English that because these particles are very tiny, they don't have much inertia to have a relative velocity to that of the background flow, so they would basically act as passive tracers, so you don't get much clustering. The same homogeneous distribution is also observed when the particles are much larger. Their inertia is much higher, so they don't per se listen to the background flow. They just follow their own trajectory. So what we do observe is a strong clustering regime when the Stokes number is order 1. So you might be thinking that this has something to do with the type of resonance with the background flow. So what I did right now was putting this non-monotonic behavior in plain English, why this is happening. But the question is, can you translate that to mathematical language? Can you come up with a framework to basically predict this non-monotonic behavior? And that's what I try to do. All right. So, but before getting too much involved with a lot of mathematics and equations, let's just start from a thought experiment. I have let's say I have a rubber strip, right? It's from some super material that I can stretch it indefinitely, right? It's not going to break. So I'm going to anchor this rubber strip at the center. So the velocity at the center is going to be 0, and I could start stretching it, right? And I'm going to do that in a way that if you measure the velocity of that rubber strip at a particular point in a space, the velocity is going to be constant, right? So basically, the way that I'm stretching it is that I'm accelerating as I'm stretching it. Now, if I put two marks on that rubber strip, and if I ask you what is going to be the distance between those 2 points as the time passes, right? You could do, probably solve this problem in 2 minutes. Just write down the equations, and you could show that because the velocity is proportional to the distance of those points from each other, they're going to exponentially increase in terms of, the long-term distance between the 2 points. With the exponent that is going to be dependent on what is the strain rate within that rubber strip, right? So I should also mention that I'm here assuming that the material within this rubber strip is homogeneous. So basically the velocity gradient at any given point is constant. Now let's make this problem a little bit more complex. So this time, instead of putting 2 markers, I'm going to put 2 rings on this rubber strip, right? So they have finite mass, and there's going to be a friction between these and the rubber strip with a force that is proportional to the velocity, to the difference between the velocity of those rings and the rubber strip. So if you ask the same question, what is going to be the distance between these 2 rings after a long period, you can solve this equation, same problem, but it might take a little bit longer. But what you will find is that, again, it's going to be an exponential increase in distance. This time, that exponent is going to be dependent not only on that strain rate, how fast I'm stretching this thing, but also the friction coefficient and the mass of those rings. Okay? Now, let's make it a little bit more complex. This time, instead of taking it and stretching it with a constant velocity, what I'm going to do, I'm going to oscillate it, right? So if you had, let's say, 2 points marked on that rubber strip, after one oscillation, it's going to come back exactly to the same point, right? But instead of using 2 markers, I'm going to have those 2 strings, two rings, right? Now you could ask the same question. What's going to happen in long term? What would these 2 rings are going to get closer to each other, or would they move away from each other? So first of all, during one cycle, you're going to have some oscillatory behavior because, that short-term oscillation motion of the rubber strip. But what we are interested in is that how do these 2 rings behave as time goes toward infinity? And if you try to solve this problem analytically, as far as I know, there is no direct solution to this problem. But you could attempt solving coming up with an approximate solution to this problem. And the interesting thing about that solution is that, again, the behavior is going to be exponential. So this time, that exponent not only depends on that strain rate, that friction coefficient, and the mass of the string, but also on the frequency that you're oscillating this thing, right? Now, by this point, you might, okay, so one more point. And the behavior that you would observe is indeed very complex. So here, what I'm showing you is the logarithm of the distance between those 2 rings as a function of time for a system where the mass of those rings are the same, the friction coefficient is the same, everything is the same, but the only thing that is changing is the frequency that I'm oscillating the rubber band, right? And you could see that in one scenario, you might get these 2 rings getting closer to each other. In certain scenarios, they might start moving away from each other at different frequencies. Well, and showing some features in that solution that might be quite non-trivial. So then you can try to make sense of what you're observing from these solutions. And what you would observe is that dominantly you're going to have 4 separate behaviors. So here I'm showing you the trajectory per se of those 2 rings as a function of time for the case that those 2 are moving away from each other in long term. So here we are going to have an exponent that is basically positive. So that's one scenario. The second scenario is that they're oscillating, but they would get closer to each other over time. So in this case, that exponent is going to be negative. A third scenario is that those 2 rings are oscillating, but also exchanging side. So in this case, you're going to have an exponent, depending on whether they're getting closer to each other or moving away from each other, positive or negative with a real component. But in this case, imaginary, meaning that the solution is going to be is going to have a component that is going to tell you how frequently these 2 rings are going to exchange side. Okay? So there are basically 4 scenarios that could happen. So by this time, you might be asking why you know, what does this has anything to do with the particle clustering in fluids? And the answer to that question is that what you're basically observing in a fluid is basically 3 rubber strips where the fluid is behaving the same way that I was describing earlier with that simple example. So if you take basically the fluid velocity gradient and decompose it to its eigendirections, basically you're going to have an strain rate that gives you the rate at which time I'm stretching or contracting that rubber strip along the eigendirections of the velocity gradient tensor. So then you could populate that with a number of particles, and the relative velocity between those particles and the fluid is exactly how those rings are going to behave relative to the rubber strip that I was using as an analogy earlier on. So the only difference would be that here these particles are being actually advected through the through the flow along a trajectory that is basically describing how that velocity gradient is going to behave over time. Okay, so now you could think that we have a flow that is, let's say, turbulent, right? So that velocity gradient along particle trajectory is going to have an arbitrary behavior per se, right? It's going to be oscillating with in a continuous spectrum with a function that then you can decompose to sets of different frequencies. But for each of those frequencies, you can try to analyze that behavior in terms of that Lyapunov exponent, the exponent that I showed you earlier, and come up with how those 2 particles, which were or rings earlier on, that I use as an analogy, how do they are going to get closer to each other or move away from each other. So this is basically saying that instead of having a single exponent that I use for one-dimensional example, here we are going to have 3 exponents in 3 principal directions associated with the fluid velocity gradient. And those would be a function of that velocity gradient, the fluid velocity gradient, along particle trajectory. So another way of thinking about this is that if you take a spherical shell and if you seed it with inertial particles, then you could track how does the volume that is basically contaminated by those particles deforms over time, right? The volume of that sphere that is contaminated by particles represent the volume that if you keep track of it and if you look at its rate of change of volume, is giving you basically the divergence of particle velocity field, which has a fundamental role in describing the behavior of whether you're going to have clustering or whether you're going to have major mixing in your flow, which turns out to be basically the summation of those 3 exponents that I mentioned earlier. So basically what I did was trying to compute that exponent for for a one-dimensional flow where we have an oscillation that contains a single frequency, and then you can combine that based on what you observe in a turbulent flow for a range of frequencies, and from that you can get a closed form solution for this problem. So there's a lot of symbols on this slide that I'm not going to explain every one of them, but I think the main takeaway message from this slide is that you could get a closed form solution for, so here I'm denoting it by C eta, which are basically the summation of those those exponents, the Lyapunov exponents, in terms of number of spatial dimensions, a Stokes number, and interestingly, Q criterion. So that's the only parameter that would link particle clustering to how flow is behaving. If you want, so this is the case that you just want to use a pen and a paper to describe the behavior of the system. But let's say if you can afford taking an integral, there's going to be another form of this solution that is a little bit more complex. It would involve the Fourier transformation of a structure function of Q criterion, this second invariant of velocity gradient tensor along particle trajectory. That if you compute that integral, is going to tell you whether your particles over time are going to get closer to each other, they're going to cluster, or whether it's going to be positive and you're going to have primarily mixing in your flow of mixing of particles or dispersion of particles in your flow. So now you may ask, does it work? And probably one of the best examples to try it on is isotropic turbulent flow in 3 dimensions. So first I'm going to show you the results where we are just using point particle direct numerical simulations. So basically I'm sitting an HIT at Reynolds number of 100 with inertial particles, and I'm computing the divergence of particle velocity field. And what you observe is makes sense with regard to what I described early on in the presentation, that you don't get much clustering at very small Stokes number or very large Stokes number. It almost goes to 0. But in the middle, you're going to have a very non-monotonic behavior. So what this means is that you're going to have main cluster, a lot of clustering at a Stokes number of order 1 when that divergence becomes negative. So this is an average quantity, which could cross over to a positive value, meaning that despite the fact that you might have a still clustering, it might give you some positive number or positive value for that divergence quantity. So the point is that you could quantify particle clustering using that only that measure, that divergence of particle velocity field. So you could also take this and use the formulation that I showed you earlier to see that whether we could predict this trend. So here's going to be the result. The black line is again from that point particle direct numerical simulations, and the blue line, some of you might be familiar with, is the formulation coming from the formulation that Maxey proposed in 1987 and applies to the regime of very small Stokes number. So with the new formulation, we do get that non-monotonic behavior. So it does show that you should expect no clustering at very small Stokes number and almost no clustering at very large Stokes number. And somewhere in the middle, you're going to have very strong clustering. Okay? The second point that I want to make is that not only it does tell you that you're going to have a strong clustering at the smallest Stokes number, but at very large Stokes number, you're going to have a strong regimes of mixing or particle dispersion, which was, which wasn't captured by some other analysis that we did earlier. Now, there are a number of caveats, which I'm going to go through some of them depending on how much time we have. And the first one is that you might say, okay, if you want to really do this, use this formulation and make this prediction, don't you need to have that velocity gradient along particle trajectory? And the answer is yes. So it's not a prediction per se that doesn't require any information from the background flow. So you still need to have that velocity gradient to be able to make that prediction. But here's an interesting point, that the solution to that equation that I gave you, which does require that, could be simplified if you ignore all that, what is that velocity gradient along the particle trajectory, and simplifying it to just single number. If you just give me what is the Kolmogorov time scale, I can produce a plot similar to this that doesn't require that information, but it still captures all the main features that you're observing in the case that we have access to that all that time-dependent information. So I think the main point here is that what we are observing in these flows, main clustering, is more to do with the solution to the Stokes-Drag equation, which if you make transformation is basically a nonlinear ODE to a harmonic oscillation, rather than what is particularly special about turbulent flow. So it's a more inherent behavior of the particles per se, rather than what turbulent is doing to those particles. The second question that may come up is that why should I trust your point particle DNS in the first place that you're using for validating your results? And that's a very valid point. I mean, the point particle DNS is making a lot of assumptions. It's assuming that particles are small enough compared to the background flow. I'm assuming drag forces to be a linear function of a slip velocity. We are neglecting added mass. We are neglecting two-way coupling forces. We are forgetting about all particle-particle interaction. So I'm not going to go over all the details, but basically, my colleagues at Stanford did this experiment where they used inertial particles, and we had a basic experimental apparatus to see the behavior of these inertial particles at a Reynolds number of ranging from 10,000 to 20,000. We did measurements at a cross section where we had inertial particles of a Stokes number ranging from 1 to 10, clustering downstream of basically a fully turbulent flow generated upstream. Later on, we made measurements of, for example, what is the variation of number density in a measured on a grid, and we did we made direct comparison of that to point particle direct numerical simulations, and what we observed is that indeed in this case, our point particle direct numerical simulations are fairly accurate in terms of capturing these particle clustering, and it wasn't because of lack of sensitivity per se. If you, for example, do not include polydispersity in this comparison, when you're post-processing your DNS result, you're going to get something that is completely different. So I think that adds certain degree of credibility to point particle simulations, but it's not conclusive. So I think that some of the conclusions that I'm going to show you later on is still required to be validated against experiments that are targeted at those particular regimes. So I have a few more minutes, and I'm going to spend that few more minutes to tell you what else did we learn from this analysis, right? It wasn't about only explaining what we observed experimentally several decades ago, something that we already knew about, or coming up with a different language of explaining the same thing that we could have explained, using plain English. But I think this is the interesting part, because it told us about a number of things that as far as I know, we didn't know about in the past. And I'm going to put that in a framework of questions and answers. Like if you were to take, for example, one parameter from the flow in order to predict whether particles cluster or not, what that single parameter is supposed to be. And this analysis tells you that the only thing that does matter, really, is Q criterion, is the second invariant of velocity gradient tensor calculated along particle trajectory. The second question that you might ask, what would happen if you go to a flow that is, the Reynolds number is very large, or the Stokes number is very large? And this analysis tells you that your Lyapunov exponent, that, or you could relate it to the divergence of particle velocity field, is going to decrease proportional to 1 over root square of a Stokes number, and it's going to increase with proportional to Q criterion to power 1/4. So these are all of these observations are those that I have also verified with point particle DNS results. But again, some of these might need to be validated using experiments. Another thing that you might ask is that if you construct a rotating flow, and what I mean by that is that basically if you calculate the norm of velocity gradient tensor, is it positive all the time? So that's what I mean by rotating flow, larger than basically the norm of a strain rate. And the answer to that question is that yes, always particles would disperse in a rotating flow. You may ask the same question about a straining flow. Do particles always cluster in a straining flow? And the answer is apparently not. If the Reynolds number, let's say, is large enough such that it gives you a Q criterion that is going to be larger than basically the frequency of those oscillations multiplied by your Stokes number. Another question that you may ask, which would be very unlikely to ask if you didn't know about this analysis, is that are those Lyapunov exponents are really bounded? Which quite to my surprise, actually they are. So basically, they cannot, there's no situation that those exponents or the rate at which those particles get close to each other is going to be smaller than -1/2, which was a very interesting observation. So this is an old one. Some of you already know, and whether particle trajectory do cross or not. This has been verified with some experiments, and the analysis shows you that actually yes, they do. The trajectory do cross if certain conditions are satisfied. And well, there's a lot more to this. I wouldn't be able to explain all of that, but if you're interested in, we have an archive version of this study that if you're interested in, please go and take a look. And at the end, I'm just going to leave you with this image that basically captures all the details that I just described. It tells you, so basically what you're looking at is the y-axis is how quickly I'm stretching that rubber band. Here you're looking at what is the frequency that I'm oscillating that rubber band. And in different points of this 2D map, you can, this is telling you whether those two rings are getting closer to each other or moving away from each other, which in this case means that whether we have clustering or whether we have dispersion, right? It tells you that where are the regions that you get basically particle trajectory, which part of the parameter space you get basically Lyapunov exponents that are equal to the lower bound that I told you earlier. Where are the regimes in which you have dispersion in a straining flow, and some very interesting behaviors that I didn't talk about, but it tells you about some very strange behaviors in the sense that if you make some very small changes, let's say in terms of frequency or in terms of the amplitude of oscillation, you might get behaviors that are drastically different, right? You could take a system where you have, let's say, particles of certain size, change the diameter by 1%, and you might go from a dispersion regime to a clustering regime. And I think that's where I'm going to stop and take any questions that you may have.
Thank you for a very insightful talk on a very complex